In this video, we'll begin our discussion of what are called initial value problems. We'll actually be doing these problems for the rest of the semester. What it does is, given a point, remember that all of our solutions are functions that have solution curves. And the solutions that we were given in that first section, some of them didn't have C, some did have C. When I have C, it's called a one parameter family of solutions, meaning the C, right? I change C, I get a new solution. That's what a parameter is, right? You choose a value for it. It's not really a variable, doesn't it? It's not an input output. It's just like a parameter would be like changing your velocity, stuff like that, like your initial velocity. And that being the parameter of your projectile motion problem. All right, so they say that is a family of solutions. It says find a solution of the first order IVP. IVP is short for initial value problem, consisting of this differential equation and the given initial value condition. So this is saying that when I plug in 1/2 into my function up here, that I will get a -4 when I'm done. So what this is going to do is this is going to allow us to take our family of solutions and use the point to find a particular solution, one solution. So how we do that is we're going to use the original function. I like to write it down so if I look back at this, I can tell where I was going. And I'm going to plug in the point that was given to us. So y of 1/2 is -4. So what we get is we have -4 equals, and it's going to be 1 over 1/2 squared plus c. So I plugged in half to the x and -4 into the y. Okay, if I keep going here, it's going to kind of keep using arrows. I get -4. Please do not use equal signs. Don't just keep doing equals. That's not, you're writing a lot of wrong statements when you do that. Just use an arrow. Okay, this is 1 over 1/4 plus c. I'm going to multiply all sides by the denominator there. So I'm going to go down here and I'm just going to draw another arrow signifying I started up there. And I got -4 times x squared plus c equals 1. Oh, and I did x squared, but it should be 1/4. All right. Now let's multiply everything, that -4 through. So I'm going to get a -1 minus 4c equals 1. All right. If I add that 1, I'm just going to work down now that I can. I'm going to get -4c. Add 1, I get 2. Right. And if you want to just stay consistent, I guess you could draw an arrow and then draw another arrow if you wanted. The only reason I drew the arrows above is because we don't usually work sideways. All right. So c then is -1/2. Now, if you're a note taker, one thing I've seen a student do, and I was like, oh, that's actually pretty smart. They would highlight these like transitions. That way they can see I went here to here. Much easier when they're reviewing for test. All right, so I got c equals -1/2. So they didn't want c though, they wanted the solution. So the solution then is y equals, and I just go back, keep my y, x squared minus 1/2. There's my solution. And then they say give the largest interval over which the solution is defined. Now, remember we can only have one open interval. I can't put multiple open intervals together. We don't want that. We just want the largest that we can. So remember when I have stuff on the bottom, I have like asymptotes here. That's what's happening, but I don't need to graph it to find it. I just want to know when is this thing going to be 0. So over here, I'm working this out. I get +1/2, and then I take the square root of 1/2, and I get the square root of 1/2. Okay, we can just leave that there. That's fine. I know in the past teachers have made you do this like, okay, that's 1 over the square root of 2, and that's going to actually just be, let's see. So that's going to be 1 over the square root of 2. If I rationalize, I get square root of 2 over 2. It doesn't matter. You don't need to go that far. You could just leave it there. Okay, so the interval then, that's where it's broken, right there. And really, it's not just there, it's a plus or minus. So I think we could do, if we have to stay, make sure that this solution is in the interval that we choose. So we had like 3 intervals here. Let me keep doing a squiggly. So our possible answers are that to the square root of the negative one half square root of one half to the positive one half square root, and then also the positive one half to a positive infinity. And we would choose the biggest out of those three if they didn't give us a particular solution, meaning the c was still there. All right. But when they give us a particular solution, I got to find where is one half. Okay. One half is definitely going to be above the square root of one half. Remember, square roots, actually, does that going to make it bigger or smaller? Let's actually check that because it kind of gets weird down there between 0 and 1. So the square root of 0.5, it actually might be bigger. It's 0.7. Yeah. So my intuition was right. Um, the 0.5 is actually not where I highlighted that. 0.5 is going to be less than that. So the interval we're talking about is right there. Yeah, so you should definitely just check those square roots. My intuition wants to tell me it gets larger, smaller, but it doesn't. Everything between 0 and 1 actually gets bigger. All right, so my solution then is right here. It is the function and the interval in which that it is defined, the largest. And the reason we had to go with that one and the other ones, and really, if we want to talk mathematically, and you're going to be like, whatever, and some of you guys may not care, this set, and that set, all three of those intervals are the same size. We'll leave that be. You mathematicians out there, you'll learn about that later towards maybe towards the end of undergrad, and then really you get into that stuff in graduate school. Different sizes of infinity and what they mean and what you can do with it. It's pretty cool. Okay, so let's do another example of this with this is a two parameter typing wrong. It's a two parameter family of solutions. Okay, they have C1 and C2 making it two. And it says find a solution of the first order IVP consisting of this differential equation. And then they give us anytime it's multiple parameters, like two parameters has to have two conditions. If it was a four parameter family, you would need four conditions and so forth. All right, so we have those two. They don't tell us to verify the solution, so make sure you're looking for that. It says find a solution. So I'm going to start with what they gave us. C1 e to the x plus C2 e to the negative x. And let's go ahead and plug in y of 1 equals 0. And let's go ahead and do the derivative too at the same time. So we get derivative is going to be C1 e to the x, nothing changes. And then we get a negative from the chain rule for the second part. All right, now we're going to plug into that one, y of 1 equals e. All right, so I'm going to create a system, meaning I'm two equations, two unknowns. That's what happens with two parameters. If we had three parameters, we would need three initial conditions, creating a system of three equations and three unknowns. That's why the number has to match. Okay, so 0 equals e to the first power is just e, so I get C1 times e plus, and then e to the first power there, so it's going to give me a c e to the negative 1. All right, the second one, I'm going to get e, that's what y is. Plugging in the first one, I get c1 times e, and then minus c2 e to the negative 1. Okay, notice we have to solve this system. This is going to require algebra, or you can use a calculator to solve these systems if you know how to use a matrix. I don't care, just solve it. So if I add down, I get e equals 2c1 e, and these cancel, leaving me with now, if I solve for C1, C1 equals, divide by e's, they cancel, and then I get 1/2. Right? How I find the next is I'm going to use that, what I just came up with, and the equation above, and you plug it in E, C1. I guess the top one would have been simpler, but I don't want to erase all that. You can use either one. I plug that in, and it's going to help me find C2. I don't want to deal with that e to the negative 1 the whole time, so I'm just going to multiply everything by e and let everything work itself out. E squared minus, and then we just get a c2. Now I don't even want to deal with the 1/2, so I'm going to multiply everything by 2. I do a lot of manipulation to just avoid things. Okay, now that's not too difficult to solve. I'm going to minus the e squared over, so I just get positive e squared equals a negative 2c2, which tells me that c2 is going to be negative 1/2 e squared. All right, so we have a c1 and we have a c2. So I can now plug that in and for my solution. So y equals, and then C1 was 1/2 e to the x, and then minus 1/2 e squared e to the negative x. And if we want, I think this is a little prettier. We get 1/2 e to the x minus 1/2 e to the 2 minus x. Remember, I just add my exponents. So that would be my final solution. Did they ask for, or usually with the solution and initial conditions, they want an interval. They probably didn't ask for it here because you can go from infinity to infinity. Because I can plug whatever I want into an e function, right? Even with the negatives and it goes to the bottom, we're going to get 1 over, I'll just leave it, 1 over e to the x, and I can never make e to the x 0. So we're never going to have any kind of domain issues with e's. Um, Unless you have e minus something e on the bottom, then when they match up, then that's when you're going to have a problem. Okay, so that's how we verify with initial conditions and to find C. This is what we're going to be doing practically the rest of the semester. Very few times will we be, I know towards the end we do practice methods without the IVP, and then I usually in homework throw 1 or 2 in there so you can keep a hold of the idea of an IVP and work more on a method. Okay, we're going to keep going forward here. I have a couple things here, the existence of a unique solution, and then we'll cut this section. I think we only need 2 videos, maybe 3. Okay, so theorem 1.21, existence of a unique solution. I think this is pretty crazy. So let R be a rectangle region in XY plane. Okay, so what that means, let's take our XY plane, and they're saying, okay, R is some region, some rectangle region, and we know it's a rectangle because they say from A to B and from C to D. So we know we're in a rectangular region that contains the point x naught, y naught, right? So that point's in that region. If, okay, and then this is the weird part, f of xy and df dy partial are continuous on R, then there exists some interval I sub 0 where I just add some number to the x's and it's contained. What I'm saying is like we're going to have some x here and there's going to be some h that I can add to both sides to say, hey, my answer's in there. Okay, so what is f though? This is going to be, they didn't really set it up here. I'm going to write it right here. You might want to add it. Dy dx, whatever's on this is going to be f of xy. All right, so whatever's on that right hand side. So if that function, so whatever that right-hand side is continuous on R, right? That means I can plug in whatever, like things connect, right? I can draw the whole thing without lifting my pencil. All I got to make sure is just nothing's going to break it. Okay, and then now I have to take the partial of that. Now, if you need to go review partials, please do. I have a Calc 3 playlist on my YouTube channel. Please go check the partial derivative section out. They're not hard. It's just kind of breaking your brain. You have to break habits. All right, so this is, if that's continuous in R, then we know there's a solution. It's kind of crazy that only if those two things, if the point's in some region, right, A to B, right, and if the function, the first derivative is continuous, and then if I take the partial with respect to y, and if that's continuous in that region, then there is some interval for an answer. So, and I know that's kind of like, okay, who cares? Some of these methods, especially towards the end, and their diffie-Qs, I think we're okay on ODEs. I'm not totally sure because it's not my field, but ODEs, um, before you start, and they may be a giant like 3-page thing that you have to do, or you have to do it numerically, which is just using like data stuff, which makes it even more tedious. You want to know if there's an answer or not, because if you can determine that there isn't one, then maybe you don't look for it. Or it's kind of nice if you can determine there is something that you're looking for, kind of makes looking for it a little easier to be motivated for, right? You know there is, you're not looking for something that may just not exist. Okay, so what does this mean? All right, it says determine a region of the xy plane for which the given differential equation would have a unique solution whose graph passes through a point x naught, y naught. So we're really only looking for this kind of interval. It's going to be just from x to x. Where on my xy plane, right? Where is it going to have a solution? Okay, so first things first here, I'm going to label a bunch of stuff. So f of xy, right, is going to be this, and I'm going to go ahead because we're going to take a derivative here in a moment. X to the 1/2, y to the 1/2. Okay, so we have that. This is continuous as long as x and y don't make a negative, right? They can make a 0, that's perfectly fine. So it is continuous on, let's define r, let's try to find r. So r would be maybe for this one, it's going to be, the x is going to be between 0 and infinity. And the y also has to be between, um, so the x and infinity. Let me do this. I think, sorry, there's several ways we could define this, different ways. So I'm trying to figure out what would be the best way. One way would be all x, y's such that, I want to say the signs are the same. So let's say if we'll say x is greater than 0 and y is also greater than or equal to 0. Or, and it's got to be both, right? It can't be the other one or the other half of the other one. So now I'm going to put this down here so I don't have to shove it in there. XY such that x is less than or equal to 0 or y is less than or equal to 0. It's one or the other, right? It can't be both. I can't have x as being one way positive and y as being negative, because if I chose x to be 3 and y to be -4, right, I got the square root of -12. That's an issue. That's making it not continuous because it's not in the real plane. So the only issues would be when in quadrants, really, we could think about it that way. Quadrant 1 and 2, you pick any point in there, you can get a y out of that, or a z, I mean. You can get a value out of that. You choose a value in here and here, doesn't work, right? It's going to come out as a negative. Okay, so we have that. And then now we have to take the partial of y with respect, sorry, f with respect to y, partial. Now remember, hopefully you guys have had some exposure to this. If not, you got to go check it out. It's just the, I really think Calc 3 should probably come before this course, or together at the same time. It's very rough, but it's doable. But if you're taking DiffyQ first, that's fine. Just go check out that section. Okay, so I take the derivative with respect to y. The 1/2 comes down. X is treated as a constant, and this just becomes a -1/2. All right, so is this continuous on that same interval? Well, we're going to get, if I were to rewrite that, I'd have 1/2 times, and I'm just going to keep it like this. Okay, square root of x over the square root of y, right? The negative moves it down. This is not continuous on that same interval, right? Because y can't be 0. So it's not going to be what I have because the y's cannot be 0 for that. X can be 0, but y cannot. So the only thing I have to change is I'm going to go in here and take away these or equal to's for my y's. So this is the answer that we were looking for. That's the region. It's either in the first quadrant off the y-axis or x-axis. X-axis is when y is 0. In the first quadrant or the third quadrant, but it can't be on the x-axis. All right, so that's where they're both continuous. These take practice. That's why I'm gonna do 4 for you. I would recommend giving yourself some grace with these, just because the idea is weird. What you guys have done so far, there isn't a whole lot of like theory-based types things, so this is probably kind of strange. All right, so one step here, we gotta have it in this form. So it's gonna be x plus y instead here. And I take a look at that. Okay, so I'm going to define my things. F of xy is equal to x plus y. And then I do the partial of f with respect to y. That's going to be just a 1. This actually, the region R, right, could be any number you want. Any x, any y. You pick your favorite point in the xy plane. I can plug it in here. I could also plug it in there because it's always 1. So they're continuous everywhere. So the region, and this is kind of weird to write out, okay? It'll be um, all xy such that x is, and we'll write it this way. And this symbol means inside of. Don't let it trip you up too much. X is either a real number, and y, not either. And y is a real number. You don't really want to say all real numbers. Actually, there's a quick way to do that. Remember the script R for real numbers? We can actually write this as well as R cross R, right? 1 point times 1 point. That's our second dimensions. And we actually can keep just adding dimensions. Upper math, we talk about nth dimensions. You go way up there. All right, so there's our region there. I'm guessing most of you guys are going to do the R cross R because it takes less writing. I don't blame you. All right, the next point. Okay, I got to get that y prime by itself. So I'm going to get x squared over 1 plus y cubed. Okay, I like to identify my functions. F of x, y is going to be that right side. And then I take its derivative with respect to y. If you want to write it in like the shorthand, primes do not exist for partials. I just graded a lot of Calc 3 exams and I saw that and it just doesn't work. What you have to do, the notation is this. I'm going to write it, actually, I'll just keep it consistent. You just put y in the subscript. That means the first derivative of f with respect to y, partial. Okay, so if that's the case, I'm going to think about this for my, I don't want to do the quotient rule. I avoid it like at all costs. Okay, the negative comes down. I make a negative x. Then I get 1 plus y cubed to the negative 2. And then it's times 3y squared. All right, I could rewrite that to clean it up if I'd like. That's going to get me a negative 3xy squared over 1 plus y cubed squared. All right, so um, we got to figure out what would be the trouble spots there. And I'm going to I'm going to highlight for a moment. It's not my answer, but I just want to look at these two. I don't really want to look at the other ones because those are a little easier. X can be whatever we want it to be, right? X is just going to be multiplied by on top, causes no issues. The trouble spot in a problem like this would be that we're dealing with fractions. I can't let that bottom number be 0. So if I were to go off to the side, some of you guys probably could just eyeball this. And I'm going to do this because it actually answers both. Okay, I want to solve when is at 0 because that's when it would cause a problem. All right, well, the square just drops off. Take a square both sides, I get 0. That's why I did the second one with the square because now it answers the first one. If I keep going, I get y cubed equals negative 1. And then remember, cubes are odd roots, just produce the same sign. So y equals negative 1 is when it would cause an issue. So this r would be all xy such that y cannot equal negative 1, right? And then let's go ahead and look up at the definition real quick. Okay, let rectangular region in the xy be defined that contains the point xy in its interior. So really, let's talk really down to the definition. Up here, it's one or the other, right? You pick one or the other. It contains whatever point, but the reason I did both is they didn't give me what the XY point was going to be. If they gave me that point, then I could have chosen one of the regions, right? And they don't overlap, so we wouldn't have a problem. The same with that second region. It's one region anywhere in there. Here, we actually have two regions, but they didn't tell me this answer down here. They didn't tell me where. So really the two open intervals that would work here would be y such, and then it would be x could be anything, but y would have to be like negative 1 to infinity, or, and this would be have to be like a whole new answer with region, or y is inside of negative infinity up to negative 1. One or the other. That's what the theorem is saying. But right now we're just finding the R that would work, and then you would use the X naught, Y naught that was given in a real practical problem to determine which one to choose. All right, so one last one here. I solve for Y prime or dy dx, whichever form it's in, and I get Y plus X over Y minus X. Okay, that's going to be my f of xy. Alright, y plus x and y minus x. Okay, and then I'm gonna do a trick here for the partial. It works. We do it in Calc 3 a whole lot. Right now, I'm gonna have to do the quotient rule anyway for the partial with y. So, but I can make it a little easier on us by doing this. Actually, that's not going to make it easier in this case. Forgive me. If I didn't have a y on the bottom, that would have made it much, much easier. So leave it alone. Forget I said anything. dy, df dy, partial. Now, I like to write these rules out, like I said in the previous section. So it is low d high, I believe. Low d high first. My brain is kind of blanking, so I'm going to go ahead. Yep, low d high. That's right. So y minus x times the derivative low d high of y plus x minus derivative of high, that's y plus x, times the second function, which is just y minus x. And that's going to be all over y minus x squared. Now, this is just a theorem. We're trying to find r. I'm actually not going to simplify that at all. The reason being is the numerator doesn't have any kind of function that I got to worry about. There's no square roots. There's no fractions on the in the numerator, so I don't have to like worry about another fraction happening. So really, all that's happening in both of these is that I need y minus x, and the square is going to take care of both. It can't be 0. So if I were to work that out, that gives me y minus x equals 0. Remember, this can't be. I guess we could do that the whole time. Y can't be x. So a region R that would work, and remember we're gonna have multiple because they didn't give us a point, be all x y's such that y cannot equal x. Right? And there's a way, there's two intervals really that exist there. We could figure out how to do that. If they were to give us a point, that would be a little easier. All right, so that's how we determine our R. It's just going to be finding the continuity of the derivative given, and then really you're finding the derivative, the continuity of the acceleration as well, or the second derivative. All right, this is hard. Give yourself some grace.